Hey, how's everybody doing? My name's Adam, and welcome to my channel Epic Epic, where I create bite-sized coding tutorials for epic results. For this tutorial, I'll be diving into concurrency and parallelization in Go. I'll be covering the core building blocks of these concepts, including Go routines, channels, and wait groups, all from the ground up in less than 10 minutes. My goal is simple. By the end of this video, you'll have the tools to start writing your own parallel programs, as well as the confidence to dig into Go's documentation to continue leveling up your understanding of these concepts. As a side note, this is my first video on the channel, so if you find the content worthwhile, please consider liking and subscribing to support me as I create more of these tech tutorials. So, without further ado, let's get into it. First, we're going to initialize our project by running the command go mod init along with your package name, which will create our go mod file. Next, we'll create our main.go file, which will be the entry point of our program. Open up your new program where we'll write our main function. Now, consider a common algebra equation like y equals mx plus b, which, simply put, lets us calculate a point on a straight line, given a value of x. Now, because I'm a modern day programmer and those Netflix shows aren't going to binge watch themselves, I have to figure out how to calculate these points with as little effort as possible. So for starters, I'm going to make a for loop so our program will iterate over a predefined set of values that we can use to plug into our y equals mx plus b equation. Although for simplicity of this demo, we're going to assume b is always 0. That way, we can always assume that we're starting at the same origin. Easy enough, right? Notice that when we first define the number of iterations we want, the program runs them sequentially from 1 to 10 in order. Now, let's add some other parameters. We'll call the next one ticks, which is the amount of times we calculate y to create an imaginary line. Then we'll define a starting slope, and after that, we'll create a value that the slope will always change by, so each iteration is a little bit different. Next, we'll define a map to record our values as we iterate through them. And the way we'll structure the map is an integer for a key that corresponds to an array of other integers, aka our y values. Inside of our for loop, we'll define our slope as the initial slope plus the change in slope multiplied by our current iteration. That way, for each iteration, we increase our slope by a constant value and guarantee a unique sequence. Next, we'll create a slice to hold our y values for each iteration. Then we'll create another loop, this time as a range because we don't have a predefined number of times to loop through the slice. Then we'll calculate y and append it to our value container slice. Finally, we'll log the output of our newly created set of y values and then push it to our results map. Let's go ahead and run through this new logic and see what we get. As you can see, we're still running through our loop sequentially, calculating a set of linearly increasing values that we can use to plot a graph or interpret trends in the data as the set grows larger. And while it's perfectly manageable for 10 iterations, what if we wanted to run 100, or 1,000, or even 100,000? At that scale, processing everything one by one becomes inefficient. Instead of running through 100,000 iterations serially, it would be far more efficient to run many of them concurrently, meaning several calculations happen at the same time. Now, we can't literally run 100,000 operations in perfect parallel unless we had 100,000 CPU cores, but most modern processors do allow for true parallel execution across 4, 8, or even 16 cores. Of course, modern GPUs can handle thousands of operations in parallel, but since Go doesn't natively run on the GPU, we'll stick to CPU-based concurrency for now. So while we may not execute all iterations at once, we can process chunks of them simultaneously, which significantly speeds things up. The more cores your CPU has, the more parallel work can be done. And Go makes this kind of concurrent processing surprisingly easy with Go routines. So let's change this logic. Before we implement the Go routine, we're going to introduce a wait group. A wait group is a way of telling our program to literally wait until we've completed all registered instances of our Go routines. Without it, we'd kick off a bunch of Go routines to process our linear plot data, but the main program would keep going, possibly exiting before any of these go routines have finished. For each iteration, we'll add a count to our wait group representing a registered go routine to be waited on. Next, we have channels. Think of a channel as a pipe that lets go routines send values back and forth. One go routine can say, "Hey, here's a value," and another one can be like, "Thanks, brother." In our case, we're creating a results channel for structs consisting of an index, int type, as well as a slice of int types, which matches the result data structure we were using earlier. Inside our iteration, we construct a value that matches the channel's expected type, containing both the iteration index and the calculated values from our y equals mx plus b simulation. We then send that value into the channel so it can be collected later. And by later, I mean after we've exited our for loop and after we've finished waiting for all of our go routines to finish, which we'll implement next. All right, so now that we've got our wait group and channel set up, it's time to unleash one of Go's most iconic features, go routines. A go routine is basically a tiny, super lightweight thread. You can start one with the go keyword in front of any function call, and that function runs concurrently with the rest of your program. Unlike traditional threads in other languages, go routines are cheap to create. You can spawn thousands, even hundreds of thousands, without killing your CPU. Why? Because the Go runtime handles all the scheduling under the hood. It's like having a tiny personal project manager deciding when each task runs. For our purposes, we're placing all of the logic for our linear data simulation inside the Go routine. This means that each simulation, from calculating the slope, generating the data points, and sending the results, runs independently in its own lightweight thread. By doing this, we can process multiple simulations at the same time, taking full advantage of Go's concurrency model. Let's run this and see what happens. Now, unlike before, when we were running your run-of-the-mill for loop, we were processing every iteration sequentially, one after the other. But now that we're using Go routines, which, again, are lightweight threads that run concurrently with the rest of your program, we're able to process multiple iterations at the same time without waiting for each one to finish before starting the next. Now, we need a way to gather all those results back into one place. That's where channels come in. Each Go routine finishes its work and then sends its result through a channel, kind of like dropping a completed report into an inbox. To follow up on our previous commitment, let's see what happens when we run 100 iterations. A 1,000 iterations. 10,000 iterations. 100,000 iterations. So just to recap, here's the full pipeline. We start by splitting up a bunch of Go routines, each one simulating a different slope for our y equals mx plus b graph. Each Go routine calculates its own data, then sends it into a channel when it's done. Meanwhile, a wait group keeps track of how many Go routines are still running and ensures we don't move on until they're all finished. Once all the data is in, we range over the channel to collect the results and use them however we want. Visualize them, export them, and build something epic. That's all I have for today. Again, this is my first video, so if you like what you see, please like and subscribe. I definitely had a lot of fun making this video, so I'm hoping to do more of these in the near future. Also, check out the link in the description to use the script for your own purposes. That's it. See you guys next time.